This call is now being recorded.
Great. So yes, we've already covered most basics about 2D vectors, including how to tell the direction or how to specify the direction of the vector using the 3 methods, which is specifying from where you're measuring the angle, or using the bearing, or using cardinal points. And well, I told you that I prefer mostly using either the bearing or method 1. I don't have a name for method 1. Probably it's out there. I just don't think there's a specific name for it. Right. And then we're just recapping for now. And then what we also mentioned is, let me see, depending on whether or not the configuration you are given, and by configuration, I mean just the arrangement of the vectors. Remember, you can either be given vectors that are joined tail to tail, right? And if you are told to use tail to tail, it means you have to use the parallelogram method, where you first draw a parallel line, a line parallel to the first vector, and another line parallel to the second vector. And where they connect, that's where the head of your resultant vector will go. So for instance, in this case, you would have the resultant vector starting here where they join, right? And then you draw it to where these parallel lines cross, right? So that's how you do tail to tail. It's also called parallelogram method. Obviously, sometimes the vectors are skewed. You find that maybe the vectors are like this. This is vector 1, and then this is vector 2, right? Let's call this v1, this v2. Let's just add those arrows to show that these are vectors. Same thing here. You would draw a parallel line, a line parallel to that guy. This line. Okay, I forgot the mathematical way of showing parallel lines, but the line I just draw is parallel to v1. Now I draw another line parallel to v2. These lines will meet somewhere. Where they meet, that's where you replace the head of your resultant. So you'll go like this. That's your F resultant, or V resultant, sorry, in this case. So that's one thing about the parallelogram method, and that's how you normally use it. Now, in another case, where instead of the vectors being connected tail to tail, you might find them being connected like this, the way we are used to, where you have the first vector, where the first vector ends is where the second, or the the succeeding vector starts, right? So like in this case, this one starts at the head of the first vector. In a case like that, whenever you draw the resultant, you use the tail to head method. The reason we call it the tail to head method is because you start at the tail of the first vector, so vector 1, you start here, and you end at the head of the last vector, vector 2. In this case, it would look something like this. So this would be your F resultant. Then usually for cases like that, obviously you need to specify the direction or theta. Same here, same there. Right. So what happens with this one where the vectors are connected head and tail? Usually you would use we call it an algebraic method of finding everything. You don't have to use scales here. You'll just use Pythagoras here, because usually this is the right angle, and you'll use tan to find theta, right? While in this case, where you have to use a parallelogram method, remember, every time you have to use a parallelogram method, chances are you have to choose a scale, because you will measure everything. You will measure this guy, the resultant. You won't calculate it. You will measure it using a ruler, like I showed you yesterday, right? And then you'll also have to measure the direction of that resultant using a protractor. So that's the difference that you would note between your parallelogram method and then this method where you're using tail to head. Okay, so that's basically everything that you need to know about 2D vectors. We also did one example, and I also showed you how to resolve vectors in general, but we will do this more today as well. You'll see more examples, okay? And then I want to just remember what else. Oh, here we were using the cosine rule. That's just maths, right? It's not necessarily a physics thing. It's maths, noticing that this is a triangle that has two sides that are known and one angle that is known between those two sides. And you know that in a situation like that, you can always use the cosine rule from mathematics. Okay, so I remember the tip I gave you there was, if you are good at your maths, physics will come very easy to you because it's all a numbers thing, okay? So yeah, here we're still doing that example. Then we did the same thing here, okay? So before we start today's examples, I want to show you something. There's something called, if you have forces, for instance, let's say you have forces like this. Usually it's three forces. It's one last property of vectors, okay? So if you have forces like this, say there are three of them, they can describe the situation to you. It can be whatever, really. They can say you have a picture hanging over, there are those pictures that are like this. Okay, I don't know what's this thing doing. My pen is misbehaving. So imagine you have something like this. This is a picture, no? Of course, I won't draw what's inside. Just imagine it's a picture frame, whatever. Some of them, they usually hang on the wall because there's a nail there and it's just hanging down. So if you draw the free body of this thing, you will get something like what I drew here. But obviously this one, let me see, it will be inverted. It will look like this. And then like that. Okay, but nonetheless, just let's use the one I drew here for now. Okay, so now what happens is when these vectors or these forces are in equilibrium, right, you can always draw a triangle. You start, and when you draw that triangle, you make sure, let me actually make these forces like that. Let's see. And then just to make a nice triangle, let's say this is F1, that's F2, that's F3. Whenever you draw it, of course, the condition is when you are told that this thing is at equilibrium. Sometimes you won't be told, but they will ask you to calculate the resultant force of these three vectors, okay? If you calculate the resultant force, and I will show you, don't worry about it now. If you calculate the resultant force of these three vectors, remember a resultant force is basically, a resultant vector, sorry, is basically a vector that represents this whole situation, but in just one vector, right? It summarizes whatever is happening here. All these forces, they are all summarized by one vector. That vector is called a resultant vector, okay? So what happens here is, if that resultant vector, as you calculate it, if it's zero, if you find that f res, we call it f res, some people just call it fr, it's up to you. If you find that it's zero, that is another way to see that this thing is at equilibrium, okay? So whenever forces or vectors are at equilibrium, their resultant vector will be zero. So here's what it means. There's this triangular law, or I'm not sure if I should call it a law. What it tells us is that, well, you can sort of draw all of these vectors into just a triangle. But when you draw the triangle, they must all be in this direction. So let me show you what I mean. See, F1 is going there, right? And then you have also F2 going there, right? That's F2. That's F1. Okay. Then you have F3 coming down there. That's F3. Okay. So this is what it basically means. You can draw all of these forces in just a triangle. Usually it's three forces. Okay. So you'll probably never actually find it where it's four forces, at least in grade 11. Okay. So in an event where a question comes and they ask you, what is the resultant of these vectors, and you read the statement and it says that these things are at equilibrium, just know that the resultant there is zero. Okay, but let's do examples and I'll show you. So this is the last basic property of 2D vectors in general. So we've pretty much covered everything. There's nothing more to know about this topic. So once you grasp this topic of vectors, right, people usually mock physics or maths, they say stuff like, but you'll never use this thing in your life. Or believe it or not, you will. And you'll use it a lot, okay? So let me give you an example before we just get to the exciting stuff. The way you would use vectors in real life, if you are a civil engineer, for instance, and you are given a beam like this, if you know beams, even in your house, the roof has something like this. Let me see. I can't remember the exact triangle, how it looks like, but it should be something like this. Right. So what happens there is you normally, if you know one thing about engineers, you have to design stuff that work. Okay. So the way they design beams is they have to analyze the forces acting on the beam members. Beam members are these things, these lines, right? So what they do is they use these vectors. So they will draw free body diagrams of all these vectors. You'll find that they have something like this. Then they analyze if the forces exerted on this beam will be what's this? Will the design work for the environment that they are designing it for? Okay. So if they find that these forces are way too much, then they have to change the design and so on and so forth. That's basically how they design beams. Okay, that's one of the ways they do it. Okay, so vectors, you will use them forever. Or anything you learn in physics, basically. Depends which career you choose as well. So don't let people say, oh, well, I did physics, it doesn't work in real life. There's no such thing. So let's get to today's work. Let me see. Where's my... I prepared some, I think 3 problems because we have to be done by 8. Let's take this one. Okay, let's start with this one actually. Excuse me. So, I think this is Eastern Cape 2025, which is last year, yes. So, if you need links to these things, just let me know on the group. I will send them to you. But it's as easy as going to Google and just searching them. So don't worry if it's not difficult to find these papers, okay? So now let's check this problem. In this problem, you have 3 forces, F1, F2, and F3. You can see all of them. And then they are applied to a crate of 25 kilograms as shown in a diagram below. So I want you to notice something. In this diagram that we're given, there's no 25 kilogram vector, okay? They would have given us like this, maybe mg, right? Where m, you know, it's mass, g is the gravitational acceleration. And then you would have to say 25 times 9.8 or 9.81, depending on which constant you guys use. So now what's happening here, the reason you're not seeing this is because this is a top view, okay? So that, what's this? That black box at the center, that's the crate. So you're looking at it from top view. So you won't see the weight of the crate basically on the free body diagram. All right. So all these forces, they are basically coplanar. Planar, which means they're existing in the same plane. It's like if you take a page or if you take a table basically and you put all of your stuff there, everything on that table, say you have your phone, your mouse, your laptop, whatever else, those things are coplanar because they are in the same plane, which is that table, right? So it's the same thing that's happening with these forces. So that's one thing I want you to know because this can be confusing, okay? You might start looking for the 25 kilogram crates, but it's actually a top view of this whole thing. Now, let's start define the term vector. So this was 3 marks. And one thing I always like to advise is make sure that you know all of your definitions before an exam because they contribute about 13%, if I remember correctly. If I'm not off, all right, I stand to be corrected, but I think it's 13% of your whole paper. So if you can remember all of them, you don't have to remember the whole year. Just 2 or 3 days before an exam, start memorizing those definitions, okay? Some of them you don't have to because it's laws that are easy to remember at any point in your life, like Newton's second law and so on. But some definitions, or even this one is easy to remember. Even if one day you decide to be something else, you will always know what a vector is. Okay. So who cares to tell us what's a vector? I won't define it for you because you should know this definition. It's the most basic definition in physics. Just unmute yourself and yeah, sing it out for us. Let's see. Guys, what's a vector? Can you guys hear me though? Oh, now I'm worried. What if I've been talking this whole time and you didn't even hear a thing I said? Let's see. Can you hear me? If you can, please react. Or you just send on the text box. Okay. Hello. Oh, Temba has an issue with his mic. Let's see. I'm not sure what's happening because I should be able to unmute you. Can anyone else does anyone else have an issue with their mic? Hello? No one. Just Temba. Yeah, I see Temba answered. Rosina answered as well. Okay. Thank you for your answers. Yes, a vector is a physical quantity with both magnitude and direction. That's true. So we can write that there. I don't want to write it though, but let's write it nonetheless. A physical quantity with both magnitude and direction. This definition is so easy. You can even teach your grade R sister or brother or cousin. They will remember it until. Right. So that's what a vector is. A physical quantity with both magnitude and direction. Right. So I want us to do something now and go to 2.2.1. We are asked to find the magnitude and direction of the resultant vector for all these forces, these three forces that we have here. Right. So here's something to always do. Whenever you're given this diagram, right, these forces, everything, step one, you make sure that all of your forces, they are resolved into their components, okay? Their X and their Y components. I'll show you how to do that in a minute. Step two, after you've resolved them into their respective components, what you then do, you group these components. You add all the X components together and you go to the Y components. You add all of them together. Now, once you have the total components, the total X and the total Y components, you use Pythagoras theorem to find the resultant force of this entire vector system that you see here. Okay, so let's do it. That's basically how you approach every problem that looks like this, basically. It'll always be the same approach. Unless if it's that situation I described earlier where the resultant is 0, then you might have to draw a triangle. But usually, every time you have to do that approach I just laid out. So let's do it. Let's start by taking this and then bringing it here. Let me just crop it. Okay. Right. So here's what happens, ne? Remember, every 2D vector has to have components. It has to have x and y components. Luckily for you, they even gave you a Cartesian plane, so you can place these x and y components nicely, right? So here's how you do it. Let's start with F1. So what I want to do now is every y component, I'll give it a red color, ne? Irrespective of whether it belongs to F1, F2, or F3. And then every x component, I'll give it a blue color or purple, I'll decide. So check this. For F1, you just draw a nice line there, right? Then that's where you will end your y component. It originates from the tail of F1. Why? Because it belongs to F1. Right. It's basically you're trying to make sure that F1 touches the Y and then it touches the X. So imagine trying to rotate this guy. You're rotating it first, that it touch the X. Okay, in this case, we started with Y. You rotate it, this pen. You rotate this thing until it touches the Y. Right. That's the first component. You only do this if it's at an angle. If it's not at an angle, you don't do it. You try to rotate it until it touches here. Okay, you're done. You found your Fy. So let's call this one F1Y. Okay, it's basically what this means is it is the Y component of F1. Okay, so depends on which textbook you use. Some textbooks may say F1, then they do this Y. It's the same thing, really. Or if you like, we can just call it F1Y. It's up to you. Okay. So I just like using this. It makes sense in science or engineering, really. So now that's F1Y. Let's find F1X now. You do the same thing. You come here, you draw a line all the way to the x-axis. If you're not given this Cartesian plane, you're going to draw your own, okay? Just to make things easy for yourself. You draw this all the way there. Then you draw a line from the tail of F1, because this vector belongs to F1. You draw it all the way there. That is our F1X. It is basically the x component of F1, okay? So what we have essentially done is F1 was like this. And now we took out its vector component. That's its y component. And then we took out its x component. So what is this thing telling you? For every vector that is 2D, which means a diagonal line in layman terms, you will always get two components, an x and the y component. And then there'll be an angle. Sometimes the angle is here, sometimes it's there. If you prefer, let's say they gave you the angle here and you want to bring it here. Can someone tell me how you would bring this angle there? Or how you would find this angle actually, given that you are given this one? You're given 30. How would you find, let me call that angle alpha. How would you find alpha? You can type it in the comments since you guys are very shy of unmuting. So yeah, how would you find alpha? This is just maths, it's not even physics. -90 minus 30, says Abigail. Okay, yes, that's very true. So if you check this whole diagram, this whole thing is a 90-degree angle. So to find alpha, you simply say alpha plus 30 is 90, right? And then you transpose, and then alpha is 90 minus 30. So what this tells me is I'm welcome to rearrange this situation anyhow, right? So that's still fine. Okay, So let's continue and find all the other components. Let's find F3. No, F2, sorry. F2, we're finding the y. We come here to the head of F2. We draw our line, and then we take a component from the tail to this line. This is our F2 y, okay? This is a y component of F2. Let's find its x. Boom, 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 boom. Okay? And then it's all the way from this side of F2. It's just that it's going over F1x, okay? So it means it's longer than F1x. It doesn't mean it's this thing. It's not this thing. Don't get it wrong. So F2 is basically like this. This is F2. And then these are the components. This is F2x. And then that's F2y. So what this also means is F2 is a resultant when you compare it to its components. If you remember, when we're finding resultants, let me see. Here, in this parallelogram method, we had parallel lines and then we would draw the resultant in between. Same as here, or let me see, there's this other one. Or here, when we did this here. So F2 is basically a resultant of its own components, okay? That's basically another way of thinking about it. Okay, so we are done with F2. What about F3? How do we resolve F3? I see Temba has his hand up. If you can unmute, you are allowed to ask a question like that, Temba. But if you can't unmute, you can just type your question. I will see it on the chat. Let me see.
Can you hear me?
Yes, I can hear you.
Yeah, so I want to see 2.2.1. My internet just disconnected.
You want to see what the question was?
2.2.1.
This is 2.2.1. Can you see it?
Yeah, have you guys already done the answer or?
No, we are working towards it now.
Okay, thanks.
Yes, sir. All right, so this is step one. You resolve everything into its own components whenever you're doing, because we're doing 2.2.1, remember. That's step one. And I'm asking you guys, what about F3? How do we resolve F3? Because step one says resolve everything into its components. No? Okay, let's continue because we don't have time. We have to be done by 5 past. Okay, what's this? 8. So F3, if you take a look at F3, F3 is just a 1D vector, right? A 1D vector, remember what I said, you can only resolve a 2D vector, not a 1D vector. Because a 2D vector exists, this thing. A 2D vector is diagonal like this. It exists in both X and Y. But a 1D vector, you can also think of it as an X component of its own self. Why? Because it's just in the X axis. It's not in the Y. So we can humbly say, I can say to you now, F3X is the same as just F3, which is 650, okay? Why? Because F3X, sorry, F3 is already on the x-axis. Let me say is just a 1D vector on the x-axis. Sorry. So there's no need to resolve it. But if it was diagonal, then we were going to resolve it. That's how it works, okay? So now we have all these vectors that we need. So step one is done. So one. We're done with step 1. Now, step 2, you write down the mathematical relationships of the, let's say, components. So now what this means is, let's start with F1. We know that F1, we'll have to move a bit fast because we've already resolved it. You have something like this, okay? This might take a lot of pages because my diagrams are big. So F1, we have something like this. And what we said is we draw lines here and you draw a line there. Okay, let me just draw it to the tail as well. And then we took F1x from the tail to where this line is. That's our F1x. And then we took F1y from this line to there. Okay, it's misbehaving this thing. That's our F1y. Now, what we want to do is to develop these mathematical relationships that we will use to then calculate everything else, okay? So we have an angle here. It's given, this angle. We're given this angle to be, what was it, 30 degrees. Now, I want you to notice something. And I think I mentioned this thing before. This right here, this thing, that thing, and that thing, that is a right angle triangle. And of course, this arrow we said is F1. So in this right angle triangle, this side of it and that side of it are the same thing. So what this means is we have a triangle that has F1x here as well. So we have something like this. Let me draw it here. If you were to think about it as a triangle, you have F1, you have F1x, then you have F1y. That's it. Then you have this angle that we're given, which is 30 degrees. Then it's a 90-degree triangle. So that's what it is. So what this tells us as well is we can then find the relationships between the components of F1 and F1. Let's start. Let's start with the vertical component, which is the y. Of F1. Okay? It's basically, if I say sine 30, I will get F1. We said vertical. I should have said horizontal, it's fine. Because I want to start with x. Remember, horizontal is x, vertical is y. Even in maths, that's how it is, okay? So those are basics that you have to know. So we'll have F1, opposite side over hypotenuse. Hypotenuse is F1. So there's F1x over F1. And we know that if we take this guy and cross multiply, remember, this is just simply over 1. And we also take that guy and cross multiply here. What we will get is that F1x. Let me just write it here so that F1x, right? Okay, it won't fit here. It's too bad. We will get that F1x is simply F1 times sine 30 degrees. Do you see it? So this is the horizontal component of F1. The horizontal component of F1 is simply F1 times sine theta. Okay, so this is how you would find the horizontal component in any diagram, any diagram. I'm not saying it will always be sine theta. You just need to relate them mathematically like what I just did below. I mean here, sorry. So what you then do for the vertical component as well is you simply go vertical component. So notice I'm doing this explicitly. For the next ones, I'll just write out the relationships so you should be able to catch on. So I'm explaining everything for this specific vector, but for the next vector, I won't explain in detail like this because it's literally the same thing. Okay. So vertical component, and I hope I'm not talking too fast, guys. If I am, you're welcome to tell me on the chat. Of F1, right? Let's go there. Vertical component of F1, we say, now how do we relate the vertical component, which is the y component, with F1 itself? Please type fast on the chat box there. Just tell me what the relationship is. What do I say? Let me give you 1 minute. At 20 past, I start.
Can you please repeat the question?
Well, I'm saying since we just found the horizontal component of F1, right? Obviously, it's an equation. How do we find the equation of the vertical component of F1? Because we already have the horizontal component. Using the same way, how do we find the vertical component now?
I think like we can simply use Pythagoras or trig ratios.
I will take the other one, trig ratios. Pythagoras, we mainly use it for...
Or when we want to find the other side when we are not given the angle.
Yes, see.
Okay.
So let's say, what's this? The trig ratio, right? So the way we would use this trig ratio, which trig ratio would we use? You're welcome to check how we did the horizontal component. I laid out every step there. So now, how do we find the vertical component using the same way?
Same ways. Let me see here.
By same way, I mean using trig ratio.
F1. F1 x. Oh, okay. So here,
This is not 300, guys. It's 30 degrees. I know my degree looks too big, but it's just 30 degrees.
let me see.
Sorry,
F1.
someone say
F1. That of F1. Let's see here.
So if you remember in maths, let me draw my triangle. Shouldn't confuse you this thing. If you have something like this, I think you learned this in grade 10, if I'm not mistaken. You have this guy, we call him the hypotenuse. We don't write it in full because, we're just lazy like that. We call this the side opposite to theta. So it's opposite to theta. Ne? We call it the opposite side. And we call this the adjacent side. Right? So these sides, they can change, these two. 1, 2, they can change depending on where you place theta. For instance, if I take theta, and instead of putting it here, I now put it there. The side opposite to theta suddenly becomes this one. So this would be my opposite, and that would be my adjacent. So you see, it can change depending on where you put theta. But what never changes is the names of these things. Okay. So let's just go back to the one I had before. theta was here. You have the side opposite to theta, which is this one. And then the side adjacent to theta, where theta is basically sitting on it, which is that side. Okay. So the adjacent side, the best way to think about it, it's where theta is sitting. So theta is resting on that side. That's your adjacent. And where theta is looking to, that's your opposite side. So we would say sine theta is opposite over hypotenuse. Right? Cos theta is adjacent over hypotenuse. You have to know these things. Then tan theta is simply opposite over adjacent. Okay. So these are the relationships that are from mathematics. We also use them here in physics, especially in this case. So we have already used this one. If you check properly, this is that. Do you see it? This is that. Sine theta, which is sine 30, is opposite f1x over hypotenuse, which is f1. Do you see? Now, how do I get f1y now? Which, because I can't use this one, because this one only gives me f1x. I have to use another trig ratio. So I must use this one, cos theta. Theta is sitting on f1y. Excuse me. So I can say cos 30 is f1y, which is adjacent over hypotenuse, which is f1. Then from here, I can cross multiply. And I can then find that my f1y, if you remember, we just cross multiply here. This is obviously over 1. You know, in math, something, a constant is always over 1. If you're not told its fraction. So if you have 2, that 2 is just over 1. If you have 3, that 3 is over 1. Unless you have something like 2 over 3, then that's a different case. That's over 3, it's not over 1. Okay. So here you can cross multiply. Bring this guy there and bring that guy here. So what you get is f1y becomes f1 times cos 30. So this, ladies and gentlemen, is my, okay, let me use this color, or this one. This right here is my vertical component. You guys get it?
Yes, sir.
Anyone else? Do you guys get it before I move on? Let me leave this triangle here. All right, so that is how you do the components. This example is taking too long. We might only do it this one only, but we will see. So do you see how we do it? Vertical component, horizontal component. We've just done, what's this, F1 for now. Let's go to F2, okay? Let's do F2. If you check F2, we are taking this basically, this thing. What we're doing is we're taking all of this. Do you see? And then what we did now on the previous one, we took all of that. And what we were just trying to do is find mathematical relationships between the vector and its components. That's what we are trying to achieve in essence. Okay, so now let's find the vertical components of F2. All right. I mean, no, the not the vertical components, but the components of F2. See this? I forgot to write F2x here. All right, so let's do it. F2, what's the angle there? 40 degrees. So I'm just redrawing the thing as it is. Please mute yourself. I think it's Innocentia. Okay. So now we have F2. Ne? This is rather too long. Let's draw it like this. Okay, can't help it. Now we have F2. This is our F2. And we are told that this angle is 40 degrees. So let's draw our lines. There's a line going there. Right. There's another line going there. Then let's draw the other one going up there. This looks like a solid line. I don't want solid lines. Okay, proper. Now let's draw the components of F2. We have the Y and the X, always. It doesn't change. But we always draw it from the tail of that vector to the line that we just drew. So let me show you. You said we'll move faster now because we just did it for the previous one. Why is it looking so weird? Okay, doesn't want, it's fine. This is what we call F2Y, from the tail to the line that connects the head of F2. Right? Now we draw the other component, the horizontal component, which is the X component. Depends on which textbook you use. Some textbooks call it the X component. Some they call it the horizontal component. So from here, I won't write all the trig ratios. I'll just write it out, the final answer. So I'll come and say, I'm looking for the horizontal component of F2. Right? Let's come here. Let's start with the horizontal component of F2, which is essentially the X component. What would it look like? Let me write it. It would be F2X is simply F2, right? Cos 40 degrees. Do you see how I did that? I simply said, I'm looking for this side, F2. How can I relate F2X and F2? This 40 is resting on this adjacent side. So that means I need a cos. Cos 40 will give me adjacent, which is F2X, over hypotenuse, which is F2. Remember what we said. This is simply a right angle triangle. This one. Where the hypotenuse side is F2. The adjacent side is F2X, and the opposite side in this case is F2Y. Notice how the sides have changed depending on the angle changing as well. If the angle was here, F2X would have been an opposite side and not an adjacent side. So it depends where theta is. Okay. So that's how we did it. Then from here, we simply cross multiplied. Boom. This was over 1. Boom. That's how I found this guy. Okay. So that's what you do. Let's go to the vertical. Remember what I said, if I'm moving a bit too fast or you are not understanding something, you're welcome to stop me and ask, like what I think it was Temba, like what Temba did. Okay. So now we have this guy, vertical component of F2 now. Boom. Notice we haven't substituted any values. We are just relating these things for now. Let's go. So we say vertical component would be, oh, this one. Yeah, it's fine. We want F2Y now because that's the vertical component. F2Y is simply f2 times sine 40 degrees. So one thing you should know, once you get one right, so for instance, we know this is 40. And it's, I'm sorry, not 40, it's cos. For us to find the f2x, we used cos. It means the remaining one has to be sine. You can only use these two, right? Whenever you're finding the components, you can only use cos or sine. So if you've already written sine for the other one, then automatically the other one becomes a cos. I see Temba's hand is up again. Yes, you can ask.
Can you please explain how you find the F2y answer for the vertical component of F2? My network just cut off.
Oh, it's the same thing we've been doing. So basically, you have this. If I take out this triangle, right? You have this triangle here. And then it's like this. So if the arrows confuse you, just write it as a triangle. You'll see that it's just mathematics. You have f2x here. You have f2y here. Then you have theta there. Theta being 40 degrees in our case. Okay. Then you have f2 here, the hypotenuse side. So I'm saying, in order to find f2y, okay, this is right angle triangle. In order to find f2y, we say sine 40, same as what we did before. Nothing changes. Whenever you find components, you will always use these relationships. They don't change. So if you practice, let's say 3 times, automatically you won't even have to write it from scratch. You'll just go straight to this equation. Trust me. It will happen. You will see. So now you have sine 40. This looks like 400. Hey, yeah, much better. So sine 40 is, remember, we said it's opposite of a hypotenuse. And this opposite of a hypotenuse is simply f2y, the side opposite to 40, the angle 40. And then hypotenuse is f2. Right, then from here, you have sine 40, right? Being f2y over f2. This is over 1. So you can cross multiply to find f2y. So for those that want it step by step, f2y times 1 is equals to f2 times sine 40. When you cross multiply, you'll get something like this. Obviously, any number multiplied by 1 is automatically just that number. It remains unchanged, okay? So f2y will just come back to being f2y. And then you'll have f2 times sine 40 degrees. So that's how we found this guy. Do you get it, Temba? Or anyone else who had the same question? Do you guys get it?
Yes, I get it now.
Thank you very much. Anyone else who's confused before we continue? You have a minute. 37, I'm starting. So guys, don't be shy. Remember, this is not a classroom. No one knows you here. Probably you guys are from different provinces or schools even. So even if you say something that you think is stupid, no one will know. No one knows your face anyway. So you don't have to be shy. Also, if you are shy, your future will also be shy. But yeah, so you don't need to be shy about these things. Now, so that's what we have. Okay. I'm encouraging you to ask. You will benefit a lot if you have a question and then you ask it, than if you have a question and you don't ask it. Okay. Now, that's what we have here. So let me remove all of this because it's wasting my space. Now, let's go to F3, the last one, before we go to our next step. We have 2 more steps to go. We do the same thing for F3. Let's go check F3. But for F3 now, F3 is already a component, if we can call it that, because it's already at X. So we don't have to find, we can't resolve F3. It's already in the X axis. So it's a 1D vector. There's no need to resolve it. You just leave it as it is. But when you relate the components, it will belong to the X components. I'll show you when we do it with the components. So we can take this as is, what we were discussing here, because this is basically what will happen. Copy. Okay, this will paste the picture as well. So weird. Great. Delete. Right, so F3 is simply, F3x is simply like that. So if we want to be ordered and do the same thing we've been doing, to avoid confusing you guys, here's what I'll do. I'll copy this guy and say, well, what is the horizontal component of F2, which is Y? Is it Y or X? Yeah, it's X, sorry. The horizontal component of F3, sorry, is this one. This is F3. This looks ugly. It's simply the same as F3. And I told you why it's like that, right? Now, what about the vertical component of F3? What about this guy? How do we mathematically represent the fact that it doesn't exist? Well, it's easy. We say F3y is simply 0 newtons in this case. No y component. Or what's this vertical component? So that's what it means, okay? Or that's how you relate it. So we've essentially now what we have done, we've resolved. What we're doing now is called resolving, where you take a vector and you break it down into simpler components. So why do we do this? We do this so that it's easy to add up these vectors, because we can group them. We can group like terms together and then add them, and group the other ones and add them. And then from there, we can then find a resultant. So in essence, what we're doing is the final resultant vector of F1, F2, and F3 is a combination of the components of the vectors of F1, F2, and F3. Let me show you how it looks like. So let's go to should be step 3, I think. Where's my blue? Step 3. Step 3, sum all y components. Let's start with y. Okay, x. We'll call them vertical components. Let me just call them vertical components to avoid confusing you guys. So the sum of all these vertical components is a resultant in itself, but it's a x resultant. So an x resultant will be a component of the final resultant. It'll be an x component of the final resultant. I'll show you what that means. So we would call this Rx. Okay. Most people call it Rx. Some you can say Fx. It's up to you, really. So when you start summing now vectors that are coming from different, or when you start summing different vectors, you have to choose a direction. You have to choose it. Whenever you sum vectors, you choose a direction. So since these vectors are lying along the x-axis like this, excuse me, we have two directions to choose from, either left or right. Left or right, because the x-axis exists. Remember, it's cut in half somewhere here. There's the positive one, which is on the right. There's the negative one, which is on the left. There is no rule to choosing this direction. You can choose it whichever way you want. You can choose to say everything on the left, I'll call it positive. That means everything opposite the left is negative. And the opposite to the left is a right direction. So that right is negative. So usually I like making my life easy. I know that in a Cartesian plane, this side is positive, that side is positive. So the upper side of y is positive, the right side of x is positive, while the left side of x is negative, and the bottom side y is negative. So when I choose directions, I just stick to these things. So let me show you what that means for me. But there's no rule to it. I just like a more convenient and consistent method. So I'll choose right as positive. So how you say it, you can either do this in an exam. That means right is positive. If you were trying to say left is positive, you would do this. Okay. Or you can write it in words. Or you can say right. No one will dispute. You chose this yourself. You know what you are doing. Now, maybe going forward, you will notice that I write stuff like this. Or I say, that's when I'm shortening positive. If I don't want to write the whole word positive, I'll simply write this positive. Okay. Or I'll write negative. So what I mean by that is I could have written this as plus VE. I just mean positive. It's something I like. Some other people do it as well, in case you haven't seen it already. So I don't want it to confuse you. So maybe going forward, I'll use that because it saves time for me. So let me take this and save it somewhere on the notes. Is it in or on? Yeah, somewhere there. Those who know English. Yeah, let's leave it there. All right, so let's start. We can now say Rx. We are adding every X component now. We are grouping them. This is what you do when you group like terms. You can do this if you want. So when you choose to write it as a symbol, you must write it next to the Rx. But when you choose to write it in words, you just write it above the calculation itself. So me now, I prefer this one, this symbol thing, because I don't have to write a lot of words, okay? It's up to you, really. So Rx is, let's sum all X components. We have which one? We have this guy, right? Number one there. We have that guy, number two. Then we have this other guy. So let's start with F1x. Rx is F1x plus F1, no, not F1, sorry. F2x, that's the X component of the force vector F2, plus F3x. That is the X component of F3. Now, where does the direction come in? Let's check where all these vectors are going. If we come to our diagram here, right, we chose this side as positive. That means anything that's going opposite to this side is negative. Let's see. F2x, is it positive or negative? Anyone care to tell me, is F2x positive or negative? It's going this way.
It is positive.
Thank you. And then what about, what else did we have? F1x, is it positive or negative?
It is still positive.
Actually, I don't like getting answers from the same person, guys. If anyone else wants to answer, just type in the comments because I assume you guys are shy with your mics. So I have one last question. F3x, which is this one, is it positive or negative?
It is negative.
Thank you very much, Innocent. So now, this is how you would do it there on this diagram. F1x is positive, right? So obviously this one will just remove this. We don't care about it. It's like when you write 2, you don't always write it as plus 2. You just know if it's 2, it's positive, unless there's something like this in front of it, then it's negative, okay? We said this one is positive, f1x. We said f2x is positive. Now f3x is the one that's negative, so we can do this. So what we are effectively saying here is we are taking the sum of all these x components, but one of them is a negative value. That's why we say plus, then we put it in brackets and say minus for it. But essentially, what it means is just simply f1x, right? You know, a minus and a plus will give you a minus. So this is the expression we end up having. So now we can start substituting. f1x, let's go back and see what it is. We said f1x is f1 sine theta, this equation here. So let's go and sub it in. f1 sine 30 degrees plus, what is f2x? f2x is simply f2 cos 40, okay? f2 cos 40 degrees minus, what is f3x? Let's go here. f3x is simply 650 newtons, okay? 650. It doesn't have an equation, it was just a value. So we still need to substitute f1 and f2. So let's go ahead and do it. What is f1? f1, there you go, 700. What is f2? 800. 800 what? Newtons. Okay. We said this one is 700 sine 30. This thing looks like a 300 degrees. This is 30 plus 800. Almost said cos. I mean sine. Cos 40 minus 650. So what answer do you get there? Please give it to me. Please punch your calculator. I can just punch this thing as it is. This whole thing. You should get an answer there. While I'm still searching for my calculator, can just find. Okay. Let me see. What do you guys get? I want to see if we found the same thing. Anyone? You can type it. You can.
I got 312.83.
I got 312.83.
I get 312.84. What is the difference between our answers? Did you get something like this? 8355. Did you get something like this?
Yes.
Yeah,
I
remember
didn't
just to round off here. Ne?
Yeah.
Yeah, don't forget to round off there. So it's 84. So notice that our answer is positive. Since this is a vector, it's not finished. Now we must add the direction. Where is it going? Is it going to the right or is it going to the left? Remember what we said. We said right is positive. So since our answer is positive, it means this vector must be going to the right as well. If it was negative, it would mean it is going to the left. So what that would have looked like, for instance, we would say minus 312.84 newtons, right? And then we won't leave it here. We will take it from here and bring it down as a positive value, but we have to specify that it's going to the left. Okay, in case if it was negative, this is what we would have done, but it's positive, so we don't have to do all of that. Good, so that's our Rx. Let's go and find on our step, will it fit here? No, it doesn't matter. Let's use another page. That's our step 4. Actually, you can combine step 3 and 4. It's the same thing. Sum all horizontal now. Now we're doing horizontal. components. And what we call these horizontal components, we call them RY. Okay. Remember what we said, we have to choose a direction. So when we choose the direction, obviously we can't say left is positive. How would we decide that? Because y is going up or down. Why would you say left is positive? So you see, you have to make sure that the direction you choose is in the same axis. So let's choose up as positive. Because like I told you, I usually use the normal convention. I don't try to make things weird for myself. That's one thing you will learn as well later on. So I'll say, because we used words the other time, you can either say up is positive or upwards is positive. Okay, so that's what we do. Now let's go. RY. What is RY now? We're summing all the y components, starting with F1y. What was F1y? It was F1 cos theta. So let's just, before we do that, let's follow the same procedure we did before. We had F1y plus F2y plus F3y. Okay. But we said this guy is 0. So we won't consider him. And then we will be left with only F1y and F2y. But are they in the same direction? Let's go check so that we don't just sum things. Ooh, you see, F1y is up while F2y is going down. So that means one of them has to be negative. Now, since we chose up as positive, which one of these two will be negative? Will it be F1y or will it be F2y? And why? I see Vigil also answered. Okay, I see your answer, Vigil. Yeah, proper. So which one will be negative between F1y and F2y?
F2y will be
Why?
negative
Why is it
because
negative?
because it is going down through the y-axis.
I can take that, but the reason I wanted was a more broader one. So here's what I wanted you to say. It is going to be negative because it is opposite to the direction that we chose as positive. And that is how I want you to think about it every time. Okay. So obviously you won't get asked why, but I want you to think about it like that because that's the right way of thinking about it. The way you answered is still correct, but it's like saying, oh, Innocentia's hand is up. Yes, Innocentia.
Sam, instead of using up and down, left or right, can I use my compass direction?
Yes.
Okay.
And then one thing I want to mention, if you are not given the direction, like in this case, you can name them. But if, let's say, this problem had specified the directions for us, we would have to stick to those directions. So let's say in the problem, if they told us that the component of F1 is northwards, and so on and so forth, then when we start choosing directions, we would have to use those type of keywords. You can't start coming with upwards when they really told you that it's northwards. That's just a small difference that you must know. Okay, so thank you for your questions, guys. Let's go. So F2y will be negative. Thank you for, oh yes, I see gift as well answered. Yes. I think some of you, the answers, they take time to reach my end. Maybe my network is a bit slower. And then we'll have, right? This is F1, y, minus F2, y. So let's substitute. F1y, where's my F1y? F1y is this guy. So it's F1 cos 30. Yo, sorry guys, my pen is doing funny things now. Maybe it's tired. Did I say sine or cos? I can't remember. Or cos. Minus f2 is what? f2y is... So f2y has to be f2 sine... Yes, f2 sine 40. Sorry if this scrolling makes you dizzy. There's no other way we can scroll. So let's substitute the values. F1 is 700. While F2 is 800. What answer do you guys get? Please give it to me. Sencha, your hand is still up. Do you have a question?
No.
Oh, okay. Just click it off.
So I got
You got what?
91 comma
Oh, let me-
91,99.
91.99. 91.99 what? What is this? It's newtons. Remember, we're dealing with force. So what I'm trying to show you is never forget your units. Ne? If you do, you won't get full marks.
Yes.
And sometimes you get the right answer, but you just forget units. So yeah, make sure. There's actually a case where it was an engineer at NASA. I think he cost them around, can't remember the exact figure, but it's there in the 900s of millions of dollars, if not 90. I can't remember exactly, but it was a lot of money. All because he forgot to mention units. So it's a huge deal. That's why they penalize you when you forget units. So since our answer is positive, it means this thing has to be going upwards. So what we have essentially done here, guys, is this. We can now draw these vectors, the ry and the rx. We said rx is 312.84. Okay, let's draw it. It's not drawn to scale, but when you draw them, you must indicate that you understand that the magnitude of the vector will tell us the length of this arrow thingy. So this is rx, ne? 312.84. Now it means I can't have ry being the same length as rx because ry has a smaller value. So remember, we represent the magnitude of vectors by the length of their body. Okay? So you can't have vectors that are of different sizes or magnitudes having the same length of arrows. So this one has to be shorter. That's what it means when they say it's not drawn to scale. But when you check the diagram, it's representative of the actual reality of these vectors. So let me, okay, you don't have to draw it dots, guys. It just makes it easy for me to visualize this thing. I don't want to teach you bad habits. Now you're drawing dots in an exam and you get wrong answers. You don't need that. I mean, you get penalized. Okay, so we have to be done in the next 10 minutes, unfortunately. So this is, yeah, it has to be our first and last example. We'll do more in our next lesson, okay? Don't despair. So this is what we've essentially done. This is ry, ne? So this is ry. Let's give it a value, 91. Wait, which diagram is this? Okay. Now, we have to find the resultant now. If you remember, there's something I said at the beginning of this lesson. Actually, even yesterday, I taught you that if vectors are connected at the tail like this, how do we find the resultant? We draw it from here to... I was going to let you guys answer, but due to limited time, we draw these parallel lines. The first parallel line is parallel to this guy. The second parallel line is parallel to this guy. Where they meet is where the resultant vector's head will be located. So let me show you what that means. Means, let me make a red color. Means my resultant will move from here all the way there. And it will be like this. This is F race. And then it will have a theta. So now, if you remember what I've been telling you this entire time, this, guys, this thing right here, it's a right angle triangle. Do you see it? This is a right angle triangle. And now, if we do it, we essentially have something like this. We have Rx and we have Ry. By the way, this side of the right angle triangle, okay, let me do this. Let me use this color. Yeah, this side is the same as that side. So I could have drawn it here as well. I would have gotten the same answer. But I draw it where there's my theta is located, so it's easy to just see everything. So this means we have Ry here, we have Rx here. As already labeled there in that diagram. It's just that I put my Ry way up there. And if it confuses you, I'm sorry, it was supposed to be here. Okay, I just couldn't fit everything. So that's how it is. And now you have theta here. And then you have F race. Now tell me, guys, this is the same, if you remember your maths, it's the same as A, B, C. And the way you find A, oh, let me redraw it here. Actually, I don't have to redraw it. We can be efficient. Copy. I was hoping you guys would tell me all of this, but if you remember, the way you find A, you can say A squared is B squared plus C squared. Then you can just square both sides, square root, and then A is simply B squared plus C. Now that is how we would find F race, the resultant we've been looking for this entire time. So that's our last step, which is step 5. Find F race using Pythagoras. This is the only theorem you will never be asked to prove. Never. Its use is more important than the proof itself. So that's why they never ask you to prove it. All right. Now, let's do it. We will say F race, can we agree, squared is Rx squared plus Ry squared from our triangle there. It's the same thing, guys. We square this side, we square root that side. F race means F resultant, basically. We just don't want to write the whole word resultant. Look at how ridiculous it looks when you write it. If you are a mathematician or physicist, engineer, whatever, you don't like stuff that look weird like that. So that's why we just write F race. All right, so Rx, we said is 312.84, right? Ry, I think it's 90, what was it? 91.99. What is this? Yeah, 91.99. And then, what answer do you guys get? Please go fast. We have to be done by 10 past.
$326.17.
326.17 newtons. Give me the units as well, Innocent. Otherwise, if I was marking your paper, I'm gonna give you a 0 for the answer. All right. I would be that harsh, by the way, guys, Units are important, very important, but one day you will learn. Okay, so now, thank you for that, Innocentia. So now, remember what I said. F res is now a 2D vector. So we can't now say it's going to right, up, left, wherever. We have to find its direction using theta, because it's a 2D vector. The resultant is a 2D vector, so we can't specify its direction using any method. Right, so this brings us to last step. Find direction using tan. So the way we find it, it's always the same, even in electrostatics and so on and so forth. No one goes and starts using sine theta or cos theta. It's just not convenient. What you do, you simply say, I know that tan theta, let's bring it to this triangle. Tan theta is simply B over C. Right? That's what you do. Then you do the arctan thing and so on and so forth. Then you are done. So we would say tan theta is Ry over Rx. Even when you do advanced maths and whatnot, tan is always y over x. Why? Because if you remember in maths, it's a gradient. It describes a gradient. So that's why we use it to find the direction of a 2D vector. So that means theta is simply tan, arctan. You see this minus 1? It means arctan, right? Ry. We said Ry is not, sorry, what is Ry? 91.99. What answer do you get? Let me see if I find the right answer too.
I got 16,39.
Thank you very much. Some people prefer to use 1 decimal when it comes to angles, but I usually prefer 2 decimals. So take note of that as well. 16.39 what?
38.
Yes, degrees.
39, I mean.
Yo, I lost you there, Temba. I think your network is not make sure. Maybe try say that again.
I was trying to say I got 16,39 degrees.
Oh, okay, thank you very much. So now to what's this? To hit the final nail. This answer is not complete. You must combine everything now. What we were trying to do is find the resultant vector. So we have to specify the magnitude and the direction of the vector. So we say therefore F res is simply 326.17 newtons. That's magnitude. Then we specify direction, which is our theta. 16.39. Some would say at 16.39. Right. So that is how you would specify magnitude and direction. So actually, this whole 9 marks, they were looking for this thing alone. Just this. Right. So let's answer the other ones just verbally because they are not as important as the 9 marks for now, at least. They are just conceptual questions. So that's 2.2.1. 2.2.2, they say magnitude of the gravitational force acting on the crates. It's just the weight. You would say weight is mg. It's the same thing I told you before, which is 25 times 9.81. Okay, this is almost 10, so you should get something like 240, I don't know, 49. I'm just estimating. What are you getting there? Or 250? Something close to 250 though. What are you getting?
It's 245.
Give me the units. Weight is measured
Newton.
in
Newton.
newtons. Thank you. So 2.3, explain why these three forces will not form a closed vector diagram. So a closed vector diagram is what I was describing at the start of this lesson, this thing here. You can only form a closed vector diagram. They also call it a triangle. I think it's a triangular vector diagram, something like that. You can only form it if the resultant force of all these vectors. Remember, we just did the same thing now. We had three vectors and we found the resultant force of all of them, which was F res, the last thing, right? If F res is equal to 0, then, only then, will you use this guy? Will you be able to draw a closed vector diagram? However, if that's not possible, then you cannot have a closed vector diagram. So based on what I just told you, do you think we can have a closed vector diagram?
No, we cannot
Why?
have a closed loop. It is because the resultant force or the net force of the system is not 0.
Thank you very much. So we would say 2.3. If anyone is left behind, do not worry, guys. We still have more lessons where we'll do vectors, okay? We have one last lesson, actually. On that lesson, I won't do, what's this? I won't do a preview like I did today because it sort of wastes our time. We'll just go straight to examples. And also, I'd like to give you a homework today, but I'll send it on the group, right? It's also about these vectors. It's a similar situation. It's just that those vectors have some interesting angles. You know, the classwork and the homework are usually a bit different. The exam is the cherry on top, right? Or the test. So what we would say here is no. Huh? Oh, no, not no, sorry. We would say because don't write long sentences. Use maths to your advantage. Because F res is not equals to 0. Simple. You get your 2 marks. Boom, boom. You can write it in words, but I am so lazy, guys. I prefer using mathematics. So because F res is not equals to 0. Oh, actually, let's do this. Because have you guys seen this symbol before? I'm not sure if it's used in grade 11. So that's why I want to use F res is greater than 0. This one is much better. So yes, guys. That is yes. You are
Can we
breaking
just
some.
use that on Euclidean geometry?
Oh, you use this one.
Yeah, on Euclidean geometry. When it
Perfect.
comes to proving.
Perfect. Let's say O because F res is not equals to 0. So you can choose either this or that. You'd get your full marks because it means the same thing. In this context, at least, it shows that you understand. So yes, guys, thank you very much for attending today's lesson. I think this brings us to a close. So whoever needs today's recording, it'll be made available once I upload everything. And then on our next lesson, we'll be doing vectors for the last time. Then we have to move to Newton's laws and so on and so forth. But also, depending on your pace at your school, we might just do vectors until maybe at your school they start with Newton's laws. So we will see. I'll keep sending those polls for you guys to just to check where you are. Okay, we don't want to be ahead of your school what's this syllabus or your teachers actually. All right, good night everyone. You can log off now. I'll see you on the next lesson. Remember, share whatever problems you face on the group, and we will happily help you. Okay. Bye.
Bye.